Our next speaker is Marcus Spradlin, and he will tell us about bespoke unitarity and colored Yukawa theory.
Thank you, Radu. It's a pleasure to be here. Thanks to the organizers for putting together a great conference. I apologize to those of you who are expecting a talk on progress and problems in N=4 super Yang-Mills theory. It's a topic that I'm still very excited about. There's been progress. There's always more problems. But as I was preparing the slides for my talk, I reflected on the fact that the last time I spoke in person at Amplitudes was 2018, where I gave a talk on Landau analysis and symbol algebras, symbol alphabets for N=4 super Yang-Mills theory. And there's been an astronomical amount of progress on those topics within the last year, even within the last week, primarily driven by fantastic young people, many of whom are in this room. So then I thought, why should I not give a talk about progress that's been done by fantastic young people? You'll excuse me if that work is all done by fantastic young people who happen to be at Brown. So I'm going to split my talk into two pieces and talk briefly about two papers that appeared a couple days ago. The archive numbers are here, but it'll really be two separate talks on two separate topics. Okay. So the first paper was called On Unitarity of Bespoke Amplitudes, and this is with Rishab Bhardwaj, Anastasia Volovich, and Hee-Chen Wen. Hee-Chen and Rishab are here, and Hee-Chen will have a gong show later this afternoon, and there'll be a poster next week. So the proximal stimulus for this work was a paper last year by Grant Remen and Clifford Chung, who provided a general construction of 4-point tree level, meaning meromorphic amplitudes that described infinite towers of higher spins with tame UV behavior satisfying dual resonance. And when you see an accumulation of words like the ones underlined in red, you start to think, okay, we're looking at something stringy here, but with almost completely arbitrarily customizable spectra. So these are somehow string-like amplitudes that are generalizations of the Veneziano amplitude. Now, their work, in turn, lies along a path that's been trodden by many papers in the last few years that explore various string-like modifications, basically exploring from the ground up or from low energy point of view, what are consistent possible deformations of string amplitudes that are consistent with all bootstrap constraints that we're aware of, and is there a sense in which we can identify mathematical or physical properties that would uniquely, in some sense, determine string amplitudes? And there's been a series of many papers, works by many people, many of them on the Kuhn amplitude, but also many different variations of Veneziano studied by Chung and Remen and others, going back many years. And working, continuing this extrapolation backwards in time, of course, leads me to the ultimate distal stimulus, which is one of, I'm using terms from anatomy there, sorry for the obscure words, proximal and distal, but one of the earliest and most famous examples of amplitudology, which is, of course, Veneziano's discovery of it. So my understanding is that these are an actual scan of his notes from 1968, where he wrote down his famous amplitude. Okay, so what are these bespoke amplitudes? Let me be briefly reviewed. They're built from two ingredients. One is you need a seed amplitude, which Chung and Remen took to be based on the Veneziano amplitude for bosonic oberst strings, and we showed you can also use an amplitude based on the open superstring, just shift it a little bit. And the notation I'm using here is that capital A sub lowercase a means that it has poles starting at where S is starting at -a, and then these are all integer spaced, of course. The second ingredient you need to define bespoke amplitudes, according to Chung and Remen, is a choice of spectral curve that generalizes the linear spectrum that we have in string theory. So in particular, the models they considered generalize a linear spectrum of mass squareds to a spectrum where the nth level sits at some ratio of polynomials that for the moment are arbitrary polynomials, except that we should take the degree of p to be larger to avoid having an accumulation point, which isn't maybe necessarily bad on its own, but in their particular construction leads to non-locality, which we don't want. Okay, so with these two ingredients, they define the bespoke amplitude as basically a Galois sum over Veneziano amplitudes, or more generally the seed amplitude. So here we take a sum over roots of this spectral curve polynomial. And so because P and Q are polynomials, when you solve for nu, you'll in general get rational functions of the Mandelstam variables. But when we take this sum over all of the roots of those polynomial equations, you'll restore the feature of having, you'll eliminate all the branch cuts. So you'll get a meromorphic function of S and T out of this process. So they showed, remarkably, they showed that when you do this, the amplitudes you get still satisfy dual resonance, which specifically by which I mean two things. First of all, that the residue at any pole in the S channel is always a polynomial in T, and moreover, that there exists a region of kinematic space, so for sufficiently negative T, where the high energy behavior is sufficiently tame that the dual resonant representation actually exists and is sensible. So this was the bespoke amplitudes that they define. And what have Rishab and Heechen done? So basically, they wanted to explore the question of whether these bespoke amplitudes are unitary, and they tested this in the crudest ramification or implication of unitarity, and that is that unitarity demands that an amplitude must have an expansion in terms of the residues. The residue polynomials that I referred to earlier must have expansions as positive or non-negative linear combinations of Gegenbauer polynomials. So we call this partial wave positivity. Okay, and it's sort of the crudest implication of unitarity. Unitarity, of course, is much more powerful than that, but this is a first necessary condition. So how did they do that? Well, by adapting a double contour integral representation for these coefficients directly from the paper of Arkani Hamed, Eberhard, Huang, and Mazera, and then using a similar very intricate contour deformation argument with the Henkel contours, etc., they were able to find and evaluate an asymptotic that is for fixed spin J and large level n. So n is the string level that you're looking at. So an asymptotic formula for large n for these partial wave coefficients. Okay, so I can summarize some of the results here. And in order to summarize the results, let me just choose a parameterization here that was also used by Chung and Remen, where you parameterize the asymptotic behavior of the spectrum for large level by saying that the nth mass level goes like some polynomial of this form, where for the moment, P will still be an arbitrary positive integer, and then it's convenient to absorb a shift here, call that the mass gap. And then these parameters here, we'll call them sort of post-Reggie parameters. There's some kind of effective parameters that tell you how you deviate away from Reggie from the asymptotic behavior. Okay, so in this parameterization, I can give you 3 slides with really quick results that we were able to derive from this asymptotic analysis. First of all, for asymptotically superlinear, that means when this polynomial is when P is greater than 1, and so this is growing faster than linearly, I call these superlinear Reggie trajectories. In this case, the coefficient of the spin J Gegenpowernomial in the nth residue polynomial is some very complicated stuff that was carefully calculated in our paper, times this, lots of stuff, but non-zero, times this really killer -1 to the j as n goes to infinity. So this tells you immediately right off the bat that there are infinitely many negative coefficients. They alternate in spin. So these models are completely ruled out by positivity or by unitarity. And this comports with, I said that later. This comports nicely with an expectation. I'll summarize that in a slide or two. Now, for exactly linear Reggie behavior, but with a shift delta, you get a more intricate asymptotic behavior like this. And you can see by looking at that formula that if delta is positive, then the second term will dominate for large n, leading again to infinitely many negative coefficients because of that factor right here. So unitarity demands delta be less than or equal to 0. And here I have to apologize slightly to Grant because although we have this formula stated correctly in our paper, there was a slight hiccup translating to the convention. Anyway, in our discussion section, we misstated how this overlaps with results of the recent paper by Nima Arkani-Hammeh. Where did the D go? I'm sorry for that as well. Chang, Figueredo, and Remen. Anyway, so this corresponds to the well-known exclusion of anything to the left of -1 here in this plot. And then finally, for the case of, this is the most interesting case. This is the case also that Chung and Remen focused on. That's the asymptotically linear spectrum. So that's the case when you have asymptotically linear behavior. So P is 1, but not exactly linear, meaning that you have non-trivial sublinear corrections. And so in this case, we have an asymptotic formula for the behavior of the partial wave coefficients. Some of it was backed up by analytical work, but also needed some numerical checks to gain confidence in the convergence of some asymptotic expansions that looked a little doubtful for a moment. So we did a lot of numerical tests. And these lead to the exclusion of a certain region in delta kappa 1 parameter space that He-Chen will mention in his Gong Show talk a little bit from now. Okay, so to quickly summarize the first half of my talk, demanding the most primitive requirement of unitarity, that being the non-negative partial wave coefficients in the large n fixed J limit, imposes constraints that complement those that you have been seen in studies at small n. For example, they allow, as I mentioned, for ruling out all asymptotically nonlinear bespoke amplitudes. And there was sort of already an expectation that this should be true from a no-go argument by Karan-Huat, Komogarsky-Skever, and Zhiboyedov a few years ago. And two, you get constraints that complement those based on multi-particle factorization, for example, as recently studied by these authors who used the highly non-trivial constraints and very powerful constraints of multi-particle factorization to rule out all asymptotically linear bespoke amplitudes in a particular case, just because I mean, with degree of the polynomial P being 2. I mean, their methods apply more generally, and there's a Mathematica package you could download, and if you're hungry for a project, you can try running their code on higher degree polynomials, and I'm sure you'll be able to rule out a lot of things as well. Okay, so that concludes the first half of my talk. Now I'm going to jump ship completely to something else. And this is about surfaceology for colored Yukawa theory in collaboration with Xiaonak Day, Andrei Pakaka, Marcos Skoronek. These three are all here. And Marcos will be giving literally the first Gong Show talk in the next session. And Anastasia Volovich, who unfortunately is not here. Okay, so this particular paper was built on 3 recent papers by Arkani-Hammeh, Hadley Frost, Giulio, Pierre-Guy Plamondon, Hugh Thomas, and also a third paper with Arkani-Hammeh, Figueredo, Frost, and Salvatori that total 178 pages. And so they could be intimidating for the unwashed masses, but of which I am definitely one, sorry. But they provide a new geometric combinatorial formalism for amplitudes in any colored theory. And at this stage, I was anticipating, and it turned out to be true, that Carolina would give a fantastic review of surfaceology. So I wasn't sure what I would do for this portion of my talk. So I thought maybe I'll just ask my artificial William Shakespeare here to write a sonnet that would summarize their papers on surfaceology. Okay, but who has time to read a sonnet? It's 14 lines long. You can go read it when you see the slides posted. You know, I admire Japanese efficiency, so I decided a haiku would be better. And this one I can read. It says, very aptly, curves count particles, hidden truths and loops revealed, physics redefined. Okay, so if you wanted to know what's in the 178 pages of their papers, well, ChatGPT has just told you. That's all you need to know. But more seriously, I wanted to view my talk as an opportunity to give a permission structure. I think that's the modern way people phrase it. I want to give a permission structure for people like me who are not in the club to jump into these papers and work on this fascinating topic. So in order to provide that permission structure, I do want to give you a review very briefly from my point of view of why this work is exciting. Okay, so Feynman diagrams in a colored theory, of course, are naturally organized by fat graph topology labeled by a genus, any number of boundaries, and then a specification of how many insertions you have on each boundary for the external particles. So here's an example with two boundaries. They're drawn in different colors, red and green, and you have 3 external insertions, 2 of them on the red boundary, 1 of them on the green boundary. So this computes a 3-loop amplitude that's a product of 2 traces, okay, because there are 2 boundaries. It has 9 internal propagators. These are drawn in purple here. They connect the 7 edges. That's just an example to set the notation. Now, fundamentally, of course, we know that every field theory is based fundamentally on cubic interactions. You can always take any higher valent interaction and build it on a cubic skeleton by introducing factors like p squared over p squared. So a goal, I shouldn't really say goal, I should say a success of the surfaceology program is to solve the underlying combinatorial problem of parameterizing the space of cubic graphs, i.e. Feynman diagrams, for any given fat graph topology once and for all. And then once you've done that, then you can go in and add in certain, they call them tropical numerator factors that will build on top of the underlying combinatorics. They will build in the numerators of whatever theory you're interested in. So specifically, the idea is to write down a sum over all Feynman diagrams of a given fat graph topology on a single curve integral. And initially, this was done just for trace phi cube theory, okay, with where you just have the propagator skeleton and nothing else. Okay, so very roughly, the idea behind this work is to Schwinger parameterize every propagator so that each individual Feynman diagram has the form of an integral over the positive orthant in capital E dimensions, where E is the number of internal edges of the exponential of minus something. I mean, you all know what that is, but just for the efficiency of writing the slides, some simple integrand integrated over the positive orthant in Schwinger parameter space. Okay, so we have a representation where each individual Feynman diagram is an integral of that form. And then what they do is, you can think about it as a giant change of variables that glues together all of these orthants into a single integral over all of capital E dimensional real space. So the sum of all diagrams is an integral over, the full R to the power capital E of something. Now I'm going to explain on the next slide why I wrote here something reasonable. I mean, it's not surprising that this is possible, right? You could just say, if there are n Feynman diagrams, even if there are Google Feynman diagrams, you could just say, well, I'm going to allocate to each Feynman diagram 1 over a googolith of the solid angle of R to the power E, and I'm going to find some change of variables that crunches that Feynman diagram's orthant into that particular solid angle. But if you just did that in some random ad hoc way, you'd get something horribly messy and completely useless and totally non-beautiful. So when I wrote here the words something reasonable, that is, the only way that this whole program could work is if you actually get something nice out of this operation. So it's not surprising that this is possible, but it is very surprising that this is actually achievable. And moreover, it's not only achievable, but it's shockingly simple, because all of the ingredients you need, you can literally just read off from the underlying fat graph topology. So remember, we're fixing a particular fat graph topology, and then we're asking for the sum of all Feynman diagrams that have that same fat graph topology. And the fundamental building block that makes all of this possible is based on drawing curves on your fat graph. So I've drawn a few examples here in purple. You saw many more examples in various guises in Carolina's talk this morning. So the curve integral in the original incarnation in trace phi cube theory looks like this. Let's work from the inside out. You have exponential of minus something. What is that something? It's a sum over all curves on your surface, certain functions called alpha that are piecewise linear and turn on certain curves in appropriate cones in RE. And then you've got a momentum P sub c assigned to each curve. Let me pause there already, because that's a little bit unusual. In Feynman diagrams, we assign momenta to every individual edge, not to every curve on a graph. So there's something slightly quite non-trivial going on there. There's a very simple rule where you assign momenta to the external edges as usual, and you assign a loop momentum to every loop as usual. But then there's a rule I didn't write down, which is that the momentum assigned to a curve is given by every time you take a turn here, you add the momenta of all of the edge coming in on the left. Well, if you take a left turn, you do nothing. If you take a right turn, you add the momentum coming in from the left. So just a very simple rule, but just slightly, slightly different from the rules that we usually use in perturbation theory. And then the remaining ingredients here are, well, the integral over the Schwinger parameter space, the L loop integration in d space-time dimensions, if you're interested in doing that. In fact, it's shockingly simple to reverse the order of these two, and there's a beautiful formula for what happens when you directly do those integrals. And then there's a subtlety that I won't mention at all. It's important, but you need to divide out by the mapping class group of your underlying fat graph in order to avoid overcounting certain cases for loop diagrams. But anyway, as I already said, everything you can read off from the fat graph. And in this paper, in this paper by Nima, Carolina, Hadley, and Giulio, they wrote a rule for how to insert appropriate numerator factors to get more interesting scalar interactions, and this was later generalized to gluons. Okay, so that's the end of my review. What was done in our paper was to ask the question, well, just in order to get our feet wet, can we try colored Yukawa theory? So can we develop a curve integral formalism for color Yukawa theory? So if you look at the poster next week, in the poster session, you'll see, or in the paper, I guess you could do that. Who reads papers anymore, right? But anyway, they worked out in explicit detail several exemplitudes at tree level 1 loop and 2 loops, both at the integrand and at the integrated level. So in order to prepare you for Marcos's Gong Show talk, which I don't want to give it all away, but I'll highlight some key features of the curve integral formalism for Yukawa theory that make it different from previous scalar theories. First of all, we now have to distinguish two different kinds of traces, right? In addition to color traces, which are in fat graph diagrams, they're just the edges of your ribbon graphs or the edges of your fat graphs. We also have, because we have fermions, we also have Dirac traces. So that requires some kind of extra decoration on top of the fat graph. And there are two distinct kinds of Dirac traces. Here's an example. You can have internal or external Dirac traces, right? So here's an example of a two-loop graph where you've got what I call this an external Dirac trace because it connects the wave functions, the Dirac wave functions for psi2 and psi1 bar, and sandwiched in there are the momenta associated to these edges. And then here in this particular example, you've got a single internal trace. This is a very simple example, just a tadpole like that, just to have something easy to draw. So you've got an internal trace where this TR now is not the color trace, of course, but Dirac trace. Okay. Now, there's a simple combinatorial rule to determine the P's. I already said it a few moments ago. And since we want these momenta to be labeled by curves, not edges, it turns out to be natural to assign each curve to be fermionic or bosonic. Again, we normally think about making every edge fermionic or bosonic, but in the curve integral formalism, it's natural to assign every curve to be bosonic or fermionic. And you'll see some examples in Marcos's talk about how to, some specific examples of how to see which curve is fermionic and which is bosonic. Also, it's natural to assign, well, you need to assign each puncture to be either fermionic or bosonic. So two different kinds of punctures. Okay, so this is my second to last slide, Radu, but we go way back. We're good friends. So, okay, there we go. That's the time. In Marcos's talk, look out for examples of the fermion-boson curve puncture assignments that I said. We need to do a sum over 2 to the L assignments of fermion or boson to the internal punctures. He'll write the explicit formulas for the tropical numerator factors. Keep an eye out for the -1 that you expect for any fermion loop. It'll be there in the slide. The numerator factor also contains a bunch of theta functions that kill certain disallowed combinations. So the color trace structure and the Dirac trace structure are intimately tied together, and many diagrams don't contribute, and those are killed by certain theta functions. And also look out for an amazing formula for post-loop integration involving certain m by m determinants, where m is the number of fermionic cones. Okay, so there are many open questions left, like can you do quarks that are in the fundamental representation instead of adjoint? Is there a naturally combinatorial way to combine the 2 to the L objects into one single object? So we already did this operation where we took all Feynman diagrams and merged them into one object. But now in the fermionic case, we still have a sum over 2 to the L different, let me not call them spin structures, but okay, yeah. It's natural to wonder if there's another formalism where one could do things differently. Is there a stringy version of Yukawa theory where you turn on alpha prime or consider delta shifts? And of course, we weren't interested specifically in the question of supersymmetry, but the theory of super Riemann surfaces is very well developed. So you could ask whether there's some nice analog of super U equations and many other questions. But I'm out of time, so I'll just leave you with a quick summary of both papers. Thank you.
Thanks, Mark, for a very nice talk. Are there any questions?
Thank you for your nice talk. I have a question about this bespoke amplitude. You said you didn't consider the accumulation point situation, but I remember Volovich wrote a paper about the Kuhn amplitude unitarity, and she also considered the asymptotic behavior of this Kuhn amplitude. So do you think this asymptotic analysis in your paper also work for?
Yeah, good. So yeah, there have been several papers analyzing the unitarity of the Kuhn amplitude, which, as you note, has an accumulation point. However, this method can't directly be applied in the Kuhn case because there isn't a double contour representation. It basically fundamentally boils down to the fact that there's no kind of Yeah, there's basically just no double contour integral representation. You need that double contour integral representation to do the large and asymptotic analysis.
Okay, okay, thank you. Actually, I write the harmonic number to solve this
Okay.
co-unitarity. Yes. Okay.
More questions for Mark? Well, as it turns out, we're right on time, so let's thank Mark again.